Good morning, guys. Today we will start our next unit, unit 5th, that is one-dimensional heat conduction and convection. Actually, sorry, one-dimensional steady state. One-dimensional steady state for your syllabus. Only steady state heat conduction and heat convection is there. So we will see. This is your 5th unit. Okay, and this unit is related to your finite elemental procedure to one-dimensional steady-state heat conduction as well as one-dimensional steady-state heat convection problems. Okay, so in these problems, actually you have studied such type of problems in your heat transfer subject. Okay, so in heat transfer subject, as we know that three modes of heat transfer. So first one is your conduction, second one is your convection, and third one is your radiation. Okay, in that actually in this subject you have studied how to determine the temperature distribution within the element or within the body. Okay, so in this subject, actually in your conduction chapter, we have studied how to determine the temperature distribution if the heat is conducted in and heat is conducted out from the body. Similarly, for convection type of problems and similarly for radiation type of problems, we have determined the temperature distribution for such type of bodies. Okay, now we will determine the temperature distribution similar to the heat transfer problems. We are going to determine the temperature distribution within the body or within the element by using our finite elemental procedure only. Okay, so for your syllabus, there are two main topics. First one is your one-dimensional steady-state heat conduction, and second topic is your one-dimensional steady-state heat convection. Okay, so for this we need to understand first the basic terms. Okay, so first basic terms is what? Suppose this is a body. Okay, as we have studied that there is a wall structure. Okay, suppose this is a steel wall and this is a copper wall, and it is conducted from this direction to this direction, and find out the temperature at the interfaces. Okay, this is like your problem. This is your T1, this is your T2, and this is your T3. Okay, if heat is conducted from this left side and it is going out from this right side, then find out if suppose this side is insulated one, then find out the temperature distribution within the element, or find out the temperature at the interfaces, at the interface of these two bodies. Such type of problems will be asked. Actually, you have studied such type of problems in your heat transfer problem. Okay, so for such type of problems, as we know that the Fourier's law, from the Fourier's law, we have determined, or we can determine our heat flux. This is heat flux. Okay, Qx is nothing but your heat flux. Heat flux going inside the body, heat flux going outside the body. Okay, so this is your heat flux, and it is given in watt per meter square because heat is going inside through this area. Okay, so watt per meter square. This is nothing but your heat flux going inside, or heat conducted, or heat going out of the body. Now this Kx is nothing but your thermal conductivity. Okay, thermal conductivity, it is given in watt per meter degree Celsius. This is your thermal conductivity, and dt by dx it is nothing but your temperature gradient. It is given in degree Celsius per meter. Okay, so Qx, it is nothing but your heat conducted inside the body as well as heat conducted outside the body, or heat going outside the body. Kx is nothing but your thermal conductivity, and dt by dx is your temperature gradient. Now Kx, why negative sign is there? Because your temperature is decreasing from left side to right side. Okay, so that's why we have taken this negative sign here. Okay, so this is the temperature gradient. Actually this is in a decreasing manner, that's why we have taken this negative sign. Okay, so these are the some basic parameters for this heat conduction. Okay, also we know that this is your Fourier's law. From Fourier's law you will get Qx equal to minus Kx dt by dx. Also the governing differential equation for one-dimensional steady-state heat conduction is given by this equation. Okay, one-dimensional steady-state equation 1D steady state governing differential equation for any type of problem is given by this basic differential equation. It is nothing but kx into d square t by dx square plus q is equal to 0. Okay. Actually, we can derive this equation also, but we actually we don't require this equation, derivation of this equation. Okay, because we are going to apply our finite elemental procedure to this equation only. Okay, so that's why we don't need to derive this equation. We can derive this equation by using this heat going out, energy going in, energy going out, then by taking the equilibrium equations, then we finally will get this equation. Actually, okay, so this is one-dimensional steady state heat generation equation. So for steady state condition, you will get the equation, but for unsteady state, you will get here some constant, or you can say rho c dt by small d. You can get this term on RHS side if the case is what? Unsteady heat conduction. But here our syllabus our syllabus contains only one-dimensional steady state heat conduction problem. So this will become 0. One steady state means with respect to time parameters, all parameters are 0. So dt by this the small dt with respect to time parameter it will become 0. So these terms will become 0, and finally this is your governing differential equation. Okay, so this is your governing differential equation for one-dimensional steady state heat conduction. Okay, so this is your governing differential equation. Now by using this governing differential equation, or we are going to apply our finite element procedure to this governing differential equation, and we will get why we are going to apply our finite element procedure to this equation. So because we need element stiffness matrix for this conduction problems. Okay, if we get the element stiffness matrix and the boundary conditions, then we can apply our previous penalty approach to this matrix system, and we will get our temperature distribution within the body. So that's why we need this equation, actually governing differential equation. Okay, similarly we are going to study our 6th unit, that is dynamic analysis. For this case we need our dynamic governing differential equation. Okay, or simple free vibration governing differential equation. Okay, so by using this free governing differential equation, we can apply our finite element procedure to this governing differential equation, and we will get what? Elemental stiffness matrix for that element. Okay, so for this we need this governing differential equation, and this is your governing differential equation. We can derive this equation also, but for time consumption or for time limit, we are taking this equation from this derivation. Okay, so and we don't need this derivation also, because this is not going to ask in your exam. So this is your governing differential equation for one-dimensional steady state heat conduction problem. Now we will apply our finite element procedure to this governing differential equation. Okay, so as we know that if we consider a two-noded finite element of the heat transfer problem, suppose this is a two-noded finite element of this heat transfer problem. So this is your first node and this is your second node. So here in our structural problems, what is the output? What should be the output? We need to define, or we need to determine displacement will be the output, or displacements will be we need to determine the displacements in structural problem. But in heat transfer problem, what will be the output? We need to determine the temperature distribution within the element. Means for first node there will be the parameter or variable will be T1, and for second node the second parameter will be temperature T2. This T1 and T2, it is nothing but temperature distribution within the element. This Qin, it is nothing but Q heat conducted inside the body or heat conducted inside the element, and Q out, it is nothing but heat going outside the element. Okay, and this capital Q is nothing but heat heat generated within the element or heat generated within the body, and it is given in watt per meter cube. This Q in or out, it is given in watt per meter square, because this is going through this area, so that's why it is watt per meter square. And this capital Q, it is nothing but heat generated inside the volume actually, so that's why the unit will become watt per meter cube. Okay, and this T1 and T2, these are the temperatures we need to determine. Okay, so as we know that if we consider the two noded element, so for first node the shape function n1 will be there. Suppose the length of that element is L. If we consider the length of that element is L, as we have derived in our first unit for one dimensional bar system or for one dimensional spring system, we have derived. In similar way we can derive for this system also, and for second node the shape function will be n. Okay, now the shape functions n1, the value of shape function n1 in similar way to the structural problems, here n1 will become 1 minus x by L, and n2 is what? X by L. These are the shape functions we are going to use for our derivation. Okay, so this is n1 is equal to 1 minus x by L and n2 is equal to x by L, as we have studied these shape functions in our first unit only. So here same shape functions we are going to apply for this heat transfer problem. Okay, now let us. Okay, so we know that by using finite element procedure, if we apply our Galerkin procedure to derive the elemental stiffness matrix, we know that from the Galerkin finite element approach, we know that it is given by x1 to x2 in bracket governing differential equation for that element into shape functions used into volume dV is equal to 0. This is the Galerkin finite elemental procedure. This is the Galerkin approach to determine the elemental stiffness matrix. So here governing differential equation is also ready. We have governing differential equation for this heat transfer problem. Shape functions also, we have shape functions Ni of x. Okay, because this is the function of x value, so we can write this Ni of x, and the volume we can write. Volume is what? This length is your dx, and this is your area for that element is A. For this surface, area is A. So volume, what will be the volume? Area into length. So area into dx is the volume. So now we can write our governing differential equation here, shape functions Ni of x here and volume A into dx into this equation, then we will get. So governing differential equation is what? So integration from 0 to length of that element L. Okay, from 0 to length of that element L. Now governing differential equation is what? Kx into d square t by dx square plus q into shape function Ni of x into volume is what? Area into dx is equal to 0. Okay, now we need to solve this equation to get our elemental stiffness matrix. Okay, so kx into d square t by dx square plus q is equal to Ni of x into a into dx into 0. So we will simplify this equation as integration 0 to L kx d square t by dx square into Ni of x plus Ni of x into area into dx plus, okay, this term into this term this first term kx into d square t by dx square into this whole term. So kx into d square of t by dx square ni of x into a dx plus similarly q times this whole term. Integration 0 to L q times ni of x into a into dx is equal to 0. So we will get two integrations here only. Now the temperature distribution T we need to write down in shape function format. So as we know that the displacement u, it is written from first unit, we can write this displacement as u1 n1 plus u2 n2. In similar way, we can write temperature distribution T as T of x is equal to T1 n1 plus T2 n. Here also u of x is equal to, we have written u1 n1 plus u2 n because we have studied this in first one. Similarly, we can write temperature distribution as T of x is equal to T1 n1 plus T2 n. So we can write this T of x is equal to T1 n1 plus T2 n2. So first we need to understand that this temperature distribution T, it is a function of x only, because this temperature distribution T is a function of x. Okay, so this is a function of x. This n, it is also a function of x with respect to integration of this T into n of dx. So it means we need to integrate this part by using our by-part rule, because these two terms are function of x, and with respect to dx we need to derive, we need to integrate this f of x dx is equal to f of x dx only. Okay, so it means what, we need to apply our by-part rule. So by-part rule is what, integration of uv du or du, you can say integration of uv, it is nothing but u integration of v minus integration of du by dx, uv dx, it is nothing but u integration of v dx minus integration of du by dx into integration of v dx. Okay, so in this way we can apply the by-part rule for this for to determine this integration. So if we consider this as a u and this term as v, so if we apply this rule to this equation, we will get, so first u into v dx, u into v dx, so u is what, ni of x, ni of x into v dx, integration of this kx d square t by dx square. Here area will become common, so area, so here we will take area as common. Okay, so what is the integration? Here we have considered this term as u and this term as v, so u integration of v dx, so u ni of x into integration of v kx into d square t by dx square, or you can say kx is also a common term, a into kx, you can take it common also. So this will become integration of d square t by dx square into dx minus integration du by dx. So du by dx, d ni of x, d ni by dx into integration of v. V is nothing but this kx we have taken common, so integration of d square t by dx square dx. Okay. So this term we will determine by using our by-part rule. By using this by-part rule, u v dx minus integration of du by dx, integration of v dx. Okay. And the remaining plus, this is kx into a is taken common plus this remaining term. So integration of 0 to L Q times Ni of x into area dx is equal to 0. Okay, so now we will integrate. Here integration is what? 0 to L, 0 to L, 0 to L. So now if we take integration 0 to L. Okay, so if we take the integration, a into kx is common. Now Ni of x into integration of this d square t by dx square into dx is what? dt by dx minus integration of 0 to L dn I by dx dn I by dx into integration of this d square t by dx square into dx is what? dt by dx into dx plus this remaining integration 0 to L Q Ni of x into a dx is equal to 0. Okay, in this way we have determined this integration. Okay, so if we multiply this akx into this term, this whole term, then it will become akx into this Ni minus akx into this term. So if we take this negative term on RHS side, then it will become, this will become positive and these two terms also become positive, but this term will be on LHS side and these two terms will be on RHS side. So same thing will be happen. Only we are taking this negative as positive on RHS side. So this will become akx Ni of x into dt by dx plus integration 0 to L Q times Ni of x into area dx is equal to a times kx integration 0 to L d Ni by dx into dt by dx into dx. Okay, so in this way we can write these terms. Okay, so here area is common. This area will get cancelled. Finally, we will get this equation. So we can write this equation on LHS side, or we can write so kx integration 0 to L dn1 dni into dt by dx into dx is equal to kx ni of x dt by dx plus integration 0 to L q times ni of x dx. Okay, so this is the final integration. So now here we need to put the values of this t as well as this ni. Okay, so ni is what? Here we have considered only one element. So for one element there are two nodes. That is I will varies from 1 to. So we will consider only for, let us say for I is equal to 1, this equation will become dn1 by dx into dt by dx is equal to k times n1 of x into dt by dx plus integration 0 to L q times n1 of x into dx. Similarly, I is equal to, it will become dn2 by dx, here n2 of x and here n2 of x. Okay, so here we will see only for I is equal to 1, and similarly we will apply for I is equal to 1. So for I is equal to 1, we know that n1 is equal to 1 minus x by n, and t is equal to what? t1 n1 t1 plus n2 t2. So t in terms of 1 minus x by l into t1 plus x by l into t2. In terms of shape functions, we need to write down. So it will become 1 minus x by l and x by l. Now we need dn1 by dx, dt by dx. Here also dt by dx. So we need dn1 by dx and dt by dx. So calculate. So dn1 by dx will become minus 1 by, because with respect to constant 0, with respect to minus x by l, it will become 1 by minus 1 by. Similarly, dt by, we need dt by dx. So dt by dx will become, here we can say dt by dx, dt by dx will become equal to, with respect to x we need to derive. Now differentiate this equation with respect to x. 1 minus x by l into t1, so minus 1 by l into t1 plus 1 by l into t2 plus 1 by l into t2. So you can write this dt by dx equal to minus t1 plus t2 divided by, because l is common, so minus t1 plus t2 divided by l you can write. So finally this dt by dx will become minus of t1 plus t2 divided by, and this dn1 x by dl is minus 1 by x. This dn1 by dx is equal to minus 1 by. Okay. Now if we put these two values into this equation, we will get. Okay. So by putting these two values into this equation, we will get kx integration 0 to l dn1 by dx is what? Minus 1 by n into dt by dx is what? Minus t1 plus t2 minus t1 plus t2 divided by n into dx is equal to kx into n1 of x into dt by dx is what? Dt by dx is what? Minus t1 plus t2 by n minus t1 plus t2 divided by n. Okay. So dt by dx is what? Minus t1 plus t2 divided by minus t1 plus t2 divided by plus integration 0 to l q times n1 is what? N1 of x. So n1 of x is what? Actually n1 is what? Here n1 of x is what? 1 minus x by l into dx. Because n1 is what? 1 minus x by l, and n2 is what? 1 by x. So we need to write down this n1 of x, 1 minus x by l into dx. Okay, so kx n1 of x into dt by dx. Okay, here we will not write this term dt by dx, dt by dx. We will put this term as only. Okay, we will discuss this term later, because we will take only integration terms. We will define only or determine only integration terms, and lastly we will look to this term. Okay, so finally what will become? So kx, only integration terms we have simplified here. Instead of dt by dx, we have written minus t1 plus t2 by l. So this will not include any integration terms, so we will take as it is. Now in this case, n1 of x will be written as 1 minus x by l, because integration will be, and because this n is a function of x1. So that's all. So this will become kx integration of 0 to L. This minus will become t1 minus t2 divided by L into L square actually into dx is equal to kx. First we will write down this term q times integration of 0 to, if we take this integration then it will become x minus x square divided by 2L or limits 0 to L. Okay, if we take this integration x minus x square by 2 times L or limits 0 to L plus kx into n1 of x dt by dx. Then finally we will write down this kx into t1 minus t2 divided by L square into integration 0 to L dx is equal to q. If we put the limits for L minus L square divided by 2L plus kx n1 of x dt by dx. Here we are only putting the limits. Finally you will get kx in bracket t1 minus t2 divided by L square into integration of this 0 to L dx. This will become x or limits 0 to L and finally it will become L into L is equal to q in bracket. Now this will become L minus L by 2. So it will become L by 2 plus kx into ni of x dt by ni of x is nothing but n1 of x. So finally for I is equal to 1 we will get this value. Similarly, okay, this L will be cancelled. So kx in bracket t1 minus t2 divided by L, or you can write kx by L into t1 minus t2 is equal to q into L divided by 2 plus kx into dt by dx at node at I is equal to 1. You can write, because this is a boundary condition. This is nothing but a heat flux. As we know that the heat flux is nothing but minus kx dt by dx. Okay. So this is nothing but a heat flux. So this is for I is equal to 1. Now for I is equal to 2, you will get kx by L in bracket minus t1 plus t2 is equal to qL by 2 plus kx dt by dx at node 2. This is again a boundary condition at node 2. This is a boundary condition at node 1. Means heat flux at node 1, heat going out at node 2. So we can write down. So finally, these two equations, it can be written in matrix form as kx into kx divided by L, or if we take this area, or if we multiply this area, it will become kx into A divided by L in bracket 1 minus 1 minus 1 1 into T1 T2. If here we are multiplying with this area A, it will become, or you can simply kx into A divided by L, because why we are multiplying this area? Because as we know that for our structural problem, elemental stiffness matrix can be written as E into A divided by L into this matrix. So in similar way, we can multiply by this area to remember this elemental stiffness matrix. Here we are multiplying by the area. So kx into A divided by L into 1 minus L minus 1 minus 1 1 into T1 minus T2 is equal to QAL divided by 2 plus area times kx dt by dx at 1 and minus kx dt by dx at, because this is going inside the element and this is going outside the element. That's why heat flux in is taken as positive and heat flux out is taken as negative. Okay, or you can write instead of this kx into dt by dx, you can write qx. So finally your equation will become kx into A divided by L in bracket 1 minus 1 minus 1 1 into this temperature vector T1 T2 is equal to Q into A into L divided by 2 plus area times Qx1 and Qx, this is minus Qx, and this is your final temperature, or we can say force and displacement in similar way, force and displacement relationship. Here temperature and heat relationship, or heat flux or heat generation relationships. So it is the elemental stiffness equation for this your heat transfer problem, where this is the elemental stiffness matrix. This is the elemental stiffness matrix for heat transfer problem. This is the heat generation rate, heat generated inside the element, and these are the heat flux. Heat flux going inside and going outside the. This is the final equation. By using this equation, now you can find out the temperature distribution. Okay. So up to this, we have derived the elemental stiffness matrix for heat transfer, one-dimensional steady state heat transfer problem. Now, in next lecture, we are going to solve some examples related to your elemental stiffness matrix for heat transfer problems. Okay. So here I am concluding this lecture.